So, today we will start module 5, and module 5 is the first of 4 modules on differential equations. So, the second part of this course will entirely be about differential equations. In module 5, we will focus on first order differential equation. So, there will be 5 lectures, each about half an hour long. In the first lecture, I will introduce differential equations, I will introduce the order of a differential equation, I will introduce first order differential equations and the basic techniques of separation of variables to solve them. In the second lecture, I will be talking about exact differentials and how they can be used to solve first order differential equations. In the third lecture, we will talk about integrating factors. In the fourth lecture, I will go to a system of first order differential equations and where you can use matrix methods to solve them, and then finally, we will end with some practice problems. So, let us get started in this. So, I will start with differential equations. Now, what are the types of differential equations? So, a differential equation is typically an equation that involves derivative. So, differential equation is a mathematical equation involving derivatives. So, now the types of differential equations. So, broadly you can think of what are called ordinary differential equations. Also called as ODEs, okay. And there are partial differential equations. This is PDEs, and really the most important thing about partial differential equations is that this has dependence on multiple variables. So, it has quantities that depend on more than one variable. This involves partial derivatives. For example, you can have a partial differential equation that looks like d square y by dx square. This is a partial derivative equal to c square dou square y by dou t square. So, this is an example of a partial differential equation, involves partial derivatives. Ordinary differential equations, in this case there is only one independent variable, and you only have ordinary derivatives. Okay, so, for example, you might have dy by dx is equal to, let us say, 3x square plus 2y. This is an ordinary differential equation. Okay. Now, in this part of the course, I will be talking only about ordinary differential equations. I will not be talking about partial differential equations, and but occasionally if you have to deal with partial differential equations, then lot of the techniques that you learn in ordinary differential equations can actually be applied in those cases also. Okay. Now, what are the examples of differential equations? Where do you see them? So, the most common examples, I mean you see them everywhere in chemistry, but one example where you are used to seeing differential equations is when you write kinetics in chemical kinetics. So, you write something like dC by dt, you might write it as k times c for a first order kinetics, etc. Or you might write or if you have multiple species, then you write C1, C2 and so on. Okay. Now, C is a function of T, this is a concentration which is a function of T, and I mean if you could have something that is looks like minus k times C of T, which is a first order decay. Other example, the classic example of partial derivatives, this equation incidentally, this partial differential equation is a form of what is called the wave equation. Okay. But the other very common partial derivatives that you are used to seeing is the time dependent Schrodinger equation. In quantum mechanics, time dependent or even the time independent Schrodinger equation. So, that typically looks like minus h cross square by 2m. This is for a single particle. Okay. So, for a single particle. So, you will have del square of psi, okay, this plus v times psi is equal to I h cross dou psi by dou t. So, this is a partial differential equation. Okay. Psi is your in this case psi is the variable, psi is a function of both r and t. R is a spatial coordinate, a 3-dimensional spatial coordinate, and time. Okay, and I am not showing the dependencies, and similarly v is also a function of r. Okay. So, this is a time dependent Schrodinger equation for a single particle, and there are many such equations. You can also write the time independent Schrodinger equation. I will not bother with doing that here. Okay. Now, I will just mention a couple of problems that you are used to when you deal with differential equations. So, there are different kinds of problems. There is what is known as a boundary value problem, where you might have something like let us take the example of the Schrodinger equation. So, if you look at the time independent Schrodinger equation, so this is time independent. So, there is no time. Okay. So, the time independent Schrodinger equation is written for a single particle is written as minus h cross square by 2 m. You have a del square psi plus v times psi is equal to E, which is a constant, times psi. So, v is a function of r, psi is a function of r, E is not a function of r. Okay. So, now this problem, this is a second order differential equation, and you need solve. So, this need boundary conditions to solve it. Okay. So, you need boundary conditions, and we will take examples of lot of these later, but this would be what is called a boundary value problem. So, a differential equation where you give the value of the function at the boundaries would be what is called a boundary value problem. Okay. Now sometimes you get what are called as initial value problems. So, you might get for example, if you have your rate law, value problem. This I will take the example of what is called a diffusion equation. So, the diffusion equation says dou c by dou t. C is a function of both spatial coordinate and a time coordinate. Okay. This is d del square c of r t. So, this is a second order differential equation, and often in this equation you prescribe the initial value. So, you say what is c of r at t equal to 0 is some function, I will just call it f of r. So, this is initial form of c of r, this should be c of r t, and this is what is called an initial value problem. Okay. So, you can have both boundary value problems, initial value problems, and essentially differential equation is related with what is called boundary conditions. Okay. So, boundary conditions are part of specification of the differential equation, and this will be clear when we write down certain differential equations. Okay. So, what are the ways of writing first order differential equation? So, I will just mention that an order of a differential equation, of an ODE, let us take an ordinary differential equation, is equal to the highest derivative. Okay. So, it is the highest derivative that appears in the equation. So, for example, if you have an equation that looks like d square y by dx square plus 2x dy by dx plus 3xy equal to 0, then this is a second order differential equations. Okay. So, first order differential equation implies highest derivative is first derivative. So, in other words, an example. So, what are the ways in which you can write first order differential equation? You might write something like dy by dx is equal to f of x y in general, some function of x y. It could be a constant, it could only be dependent on x, it could only be dependent on y, but it is some, in general, some function of x and y. Okay. So, this is one way you could write it, but there are other ways also you can write it. You might have a differential equation where you do not write it separately like this. You might write it something like, I will just write it in this form. So, I will just say some function of x, y and dy by dx equal to 0. So, this is another way of writing differential equations. So, this is so an example of this would be example, suppose you have 2x dy by dx whole square plus 3y dy by dx plus 4x equal to 0. So, this is some function of x, y and y prime, and that is equal to 0, and notice that even though you are squaring this derivative, the highest derivative that appears is 1. So, it is actually a first order differential equation, okay, and so you can have it in this form also. A third way, which is often very useful, is to actually consider something like this. So, imagine that you have a ratio of two functions and then you multiply it out and you write it in the form. So, you write it as m of x y, m is some function of x y dx plus n of x y dy equal to 0. Okay. So, I am rewriting the differential equation in this form. Okay. So, this is another possibility that you can have. So, you can often rewrite the differential equation in this form. So, basically there are different ways in which you can write the same first order differential equation, okay, and we will use each of them and we will choose which one is more convenient for our case. Okay. Now, a few more things I want to mention. So, what is a linear differential equation? Implies highest algebraic power of dependent variable or any of its derivative equal to 1. Okay. So, a linear differential equation means the highest algebraic power of the dependent variable or any of its derivatives is equal to 1. So, for example, you could have a differential equation that looks like, let us say dy by dx plus 3xy plus 2 dy by dx into x square, okay, equal to 0. So, this is a linear differential equation because each term has y raised to 1. So, this has dy by dx, this has y, this also has dy by dx. You could even have a d square y by dx square it would still be a linear equation. So, whatever derivative you have no power of that is greater than 1. So, as opposed to, so this is a non-linear, I will write a non-linear differential equation. So, this for example you could just have dy by dx equal to 3y square, okay, 3y square. So, now y square is a non-linear term, okay. So, it depends on y to the power 2 greater than 1. So, this is a non-linear differential equation. So, linear differential equations have either y or its derivative only up to the first power, okay. So, these are the kinds of equations that you have, okay. And now what do you do with the differential equation? You solve it, okay. Now there are different things that you have to keep in mind while solving it, okay. Now when you solve the differential equation, so suppose let us take we will consider the case where y of x, okay, y is a function of x, and this is the y is the dependent variable, and x is the independent variable. And let us say my differential equation f of x y prime equal to 0, where y prime equal to dy by dx, okay. So, this was one of the ways we could write the differential equation. So, this is the differential equation that we consider, okay. Now, if you consider such a differential equation, so the solution can be either explicit, that means y is equal to some I will just say g of x, okay. So, that is an explicit solution. So, in an explicit solution you have your left hand side is y and your right hand side is some function of x, okay. So, when you solve it, you say that this is the solution. Or you could also have an implicit solution where you do not actually separately write y equal to something, you have some function of x and y equal to 0, okay. So, an example, suppose you have dy by dx equal to cos x, okay. Then when you solve this, you will write y is equal to sin x plus some constant, okay. This is an explicit solution, okay. On the other hand, if you have something like dy by dx is equal to minus y divided by x plus y, okay, multiply it out, you will write x times dy, okay, and then you have plus y times dy, and then you have is equal to minus y times dx, and you can write the solution by bringing this dx to the left. So, you will have something like x dy plus y dx plus y dy equal to 0, and what you realize is that this is just d of x y, okay. This is just d of x y. So, when you integrate this, you can show that x y, and this is d of y square by 2. So, plus y square by 2 equal to 0. So, this is an implicit solution. So, you can have both explicit and implicit solutions for differential equations. Now, the other point about differential equations is that you can have general solutions and particular solutions. So, we already saw here. So, if you look at your differential equation, if you look at this differential equation, dy by dx is cos x, okay. Now, we have y equal to sin x plus a constant. So, I will just write it again. So, dy by dx is equal to cos x, then you say y is equal to sin x plus a constant. This is a general solution. because I can take any value of that constant and it will still satisfy this differential equation. So, any choice of this constant will still satisfy the differential equation. So, this is called a general solution. Okay. On the other hand, if you have a differential equation that does not have any arbitrary constant, okay, then you call it a particular solution. So, a general solution has arbitrary constant okay. Now suppose I take the same differential equation equal to cos x, but I give some boundary condition y of 0 equal to 0. Okay, suppose I say y of 0 is 0. So, this differential equation with this boundary condition, okay, then you will say that y is equal to sin x plus c. Okay. Now, you will say y of 0 equal to 0, that means 0 equal to sin 0 plus c implies c equal to 0. So, the particular solution has the form y equal to sin x. Okay. So, this is the particular solution, it has no arbitrary constant. Okay. So, you can have both general and particular solutions of differential equations. Okay. So, now what is the general strategy for solving differential equation? So, the first thing that you try to do when you get a first order differential equation is to separate variables. Okay. So, for example, if you have dy by dx is equal to 3xy, okay, plus let us say 2x, I will just say 3xy plus 2x, okay. Then what you will do is you will try to write this in the following form, you will write it as dy by dx is equal to x times 3y plus 2. Then what you will do is you will write dy divided by, you will collect all the y terms on one side, 3y plus 2 is equal to x dx. Okay. And once you do this, then you have the solution of the differential equation, because you can integrate both sides independently. Okay. Then you integrate both sides. So, when you integrate both sides, when you integrate the left hand side, integral dy divided by 3y plus 2. Okay. So, integral 3y plus 2, this is just equal to log of 3y plus 2 into 1 by 3 divided by 3. Okay. So, log of 3y. So, if you take the derivative of log, you will get 1 over 3y plus 2, and then the derivative of 3y plus 2 is just 3. So, log of this divided by 3 is exactly this quantity. And what about integral x dx? This is just x square by 2. Okay. So, I can write so if I integrate both sides, okay, then I will get something like log 3y plus 2 divided by 3 is equal to x square by 2. Now you can always add an arbitrary constant, because you take derivative of a constant, you get 0. Okay. So, I can always add an arbitrary constant of integration. Okay. So, I can rearrange this to write this as 3y plus 2 log of 3y plus 2 is equal to 3x square by 2, okay, plus 3c is some other constant c prime, I will just call it some other arbitrary constant c prime. Okay. And if you want, you can even go one step further and you can write 3y plus 2 is equal to e raised to 3x square by 2, and then you have e raised to c prime. So, I will just call it e raised to c prime. Okay. And e raised to c prime is another arbitrary constant. Finally, I can write the whole thing as 3y plus 2 is equal to some constant a e raised to 3x square by 2. Okay. And if you want, I can further write y equal to something. Okay. But this is a general strategy of solving differential equation. You try to separate variables, you try to get one side having only x and one side having only y, and then you integrate both sides. Okay. So, this is the basic strategy, but sometimes you cannot do this separation. So, we need other methods. okay, which is what I will discuss in the next class.